fourth lecture, the 4 lectures of special theory of relativity, we have now worked out the structure of the new theory, and we have seen the unusual consequences that come out of that is in terms of length contraction, time dilation. We have studied how the velocity addition rule changes. We have talked quite a bit about the simultaneity of events and have explored a funny phenomenon like this twin paradox. And also we have studied an application in Doppler effect, how to deal with Doppler effect in a relativistic manner. What we haven't really done so far is to look into the dynamics, because ultimately when you are going to modify or generalize the Newtonian formulation, you have to have a clearly written set of things, set of equations to represent that. And the representation should be such that we recover the Newton's law in the suitable limits. Okay. So before we start, first point is that why do we really need to modify? What are the, before going into, of course, when we have written down a whole new set of equations, it's kind of no-brainer that there will be impacts in all the conservation laws, their structures, and Newton's mechanics, that is Newton's law. I would request the person who has on microphone to turn it off. Okay, so let me now share my screenshot. So first, what we will do is we will first briefly uh, set the set the motion rolling, that why we need to modify the Newton's law. What are the issues that we need to tackle? Because that makes the case of why we are going to do what we are going to do next. So can you see the screen?
Yes, sir.
Yes, sir.
Great. Nice. So these are the questions I'm going to pose. Why do we have to modify Newtonian mechanics? And when you say that we are going to modify Newtonian mechanics, which laws are you going to modify? So the first thing that comes into mind is that the second law of motion, okay? That force is equal to rate of change of momentum. What happens to that? Does anything happen? And then the important stuff, the conservation laws of momentum and energy. What happens to them? How do we generalize them? Okay. Now, to answer the first question, why do we need to modify the Newtonian mechanics? So here are a few bullet points that you see the Newtonian mechanics is inconsistent with special relativity because the laws of Newtonian mechanics are invariant under Galilean transformation and not under the Lorentz transformation. One can easily see that even without doing calculation, one can understand it the following way, is that as a derivative of the Newtonian mechanics, you calculate the relative velocity, right, in different frames. So there goes the second bullet point, that in Newtonian mechanics, a force can accelerate a particle to indefinite speeds, whereas special relativity limits the maximum speed of anything to that of speed of light. So therefore, Newtonian mechanics, under the framework of Lorentz transformation, has a problem. Now, moreover, in classical mechanics, action at a distant forces are permitted, while requiring the action and reaction forces be equal. That's the third law, right? So such equality of action and reaction has no meaning in special theory of relativity except for contact forces, because the simultaneity of separated events is relative. When you are talking about action at a distant forces, so you are saying that every force has its equal and opposite reaction. What you implicitly mean that they are happening simultaneously. You have an action and immediately at the same instant there is reaction. That's the Newton's third law. But we already have seen that the concept of simultaneity is relative. There is no absolutism in each. Only in case of contact forces where things are simultaneous, really simultaneous, simultaneously happening. That is, at a very instant, at a particular instant, there is a contact, and that's it. Then only the simultaneity of separate events can still be considered. So all this point out to the fact that we need to generalize the laws of mechanics and other principles such as momentum conservation, such that in the limit when v by c is much less than 1, we recover Newton's laws of motion and classical momentum conservation, for example. Now, why v by c is less than much less than equal to 1? Because by example, in the previous class that we worked out, we already found out that the in case of by c much less than equal to 1, the Newtonian mechanics, as we know, it holds, and the phenomena that we can easily relate to our day-to-day experiences also hold, but does not hold when V is of the same order as C. So therefore, in order to justify our new formulation, we always have to cross-check against the limit of V by C much less than 1. And if we can recover the Newtonian mechanics, the offshoots of Newtonian mechanics, then we can safely say that what we have formulated is correct. As you have seen that for Lorentz transformation, that was true. For velocity addition, that was true. Even if you do it in case of Doppler effect, that will be true. Okay, so that's the point. Now, how we are going to do it? So we will be see there is a very elegant formulation, very nice elegant formulation regarding this conservation laws, which is known as the 4-vector formalism. It's a mathematical formulation, but that takes care of the invariances in the framework of special theory of relativity, and all these space and time coordinates and momentum and energy components, those can be put under a single framework. It's a very elegant one. But today, we are not going to do that. We first go in a kind of little conventional way, which is less economic, but at the same time, I would think that this would be more powerful in convincing people who are dealing with this subject for the first time. So what we are going to do is we are going to start by studying collisions. Okay. Why do we do collisions? Because collision is a contact kind of forces. So it would be most appropriate. So here we will assume that the interaction between particles take place only during an infinitesimally short time interval in which the particles have negligible separation. And during the collisions, the particles are accelerated, but before and after the interaction, there is no acceleration. So try to understand this, that the time of this interaction is so hell short that even though the particles can accelerate, but they can accelerate within this time, before and after the interaction, which we are going to study, there is absolutely no acceleration. Okay. Now, we know that the laws of conservation of momentum and energy are valid classically during this interaction. If we require that these conservation laws are also valid relativistically, and hence they can be general laws of physics, we must modify them from the classical form so that under this condition that V by C is much less than 1, we get back the Newtonian form, the classical forms of the conservation laws. Okay. So all that points out towards the fact that we need to redefine momentum. Because when we do study this collision problem, elastic collisions, for example, the momentum conservation law is paramount in getting the equations of motion or understanding the motions. Okay. All right. So here we go. So here is our collision problem. So we are going to focus on the conservation of momentum here, and we are going to find out that what are the modifications needed to preserve this principle in the relativistic mechanics. Okay. All right. So here you consider an elastic collision between two particles, identical particles A and B. Okay. And it's just a grazing elastic collision, means they are just kind of touching each other and leaving them. You can see the trajectories is sort of, although it's a cartoon diagram, but this tells the story. So it's elastic collision. The collision is symmetric. Relative velocity of the frames fixed to A and B is V. Each particle has the same speed u naught in its own frame before the collision. Okay. And the effect of collision is to alter velocities in y direction only. So with this, we are going to study the problem. Is this clear? The statement of the problem?
Yes, sir.
Okay.
Yes,
Yes,
sir.
sir.
All right. Now, see,
Can you please explain the third point?
Sir, how can
relative
particle
velocity
have speed in its own frame?
they can't have. Nobody can have speed in its own frame. You cannot measure a speed of something in your own frame.
Yes, sir. Like in its own frame, particle should be at rest.
No, not necessarily. Not necessarily. You still can have motion in your own frame. See, there are two things. One is, suppose this thing. Okay, imagine this. You are in a frame which is a platform, a railway platform. That is one frame, right? And then there is a train going. Okay, there is an observer on the train sitting. So he is the observer. So he's sitting on the train, and then a person is running on the train, right? So what would the observer on the train say? That the person has a velocity with respect to train or not?
Yes, sir.
Yes, sir.
So that's the same thing.
But the person sitting in the train, he will not say that he has a velocity. So
No,
here
he
it
is
is
not
written.
saying. He is not saying. I didn't say that he is saying.
So
See,
the
that man.
observer's frame, in his observer's frame, he himself will be at rest, right?
Yeah,
Always.
the observer's frame and the particle has the same speed in its own frame, means that there is an observer who is not the particle, who is observing the speed, measuring the speed. Okay,
Okay.
still
Okay,
not
sir.
clear.
Not really, sir. So what is like?
So what you are
So
thinking is
then
that
why is it said in its own frame?
a frame. So tell me this thing, that the man that is running on the train, his speed, can't he have a speed in his own frame?
No, sir. In his frame, he is stationary.
How come?
Because sir, because it is his frame, right? So the train is moving in his frame,
No,
but
no,
he
no,
is
no,
stationary.
no, not at all. See, in his own frame, he is running from front to the end over a period of time. He is crossing a distance. That distance he is measuring in his own frame. That distance is not the same distance as measured by an observer in the outside platform.
Yes, sir. But for him, it is the train that is moving, right? He in his own frame, he will always be
In
stationary.
his own frame is the train. In the train, he is moving. If a person is sitting in the train, he can say that I am not moving because my displacement is zero. But for this guy who is running, he can say that I have actually crossed in my own frame in this time, this amount of length.
So in his frame does not mean he is the observer.
No, that's what I'm saying. He is not the observer.
So what is his frame, sir?
His frame is the train frame.
Actually, sir, if we consider it on a large scale, suppose we are considering a person sitting on planet Earth and the same train moving. So in that case, a
Mm,
train would be having its own velocity in its own frame, and the person sitting
mm.
on the Earth will have a stationary would have no velocity, and similarly, the observer sitting in the train will have a velocity.
As opposed to whom? How do you measure velocity?
Uh, Sir, as you suggested, what I understood, what from what you are saying, that in this problem, in his own frame means the train.
The train. The train is the frame.
And now, if we consider
So
that
in
planet
the
Earth is
train,
a frame,
in the in the train, somebody is sitting. Okay, and after a finite time, what would he say? What is his velocity?
zero.
Zero, because there is no displacement. But during this time, he has measured that a person has moved throughout the length of the compartment. So what would he infer? That fellow has a velocity or not?
So, according to that person who's sitting in the train, the
Mhm.
person would be having a velocity. That I agree, sir. But
Right.
according to the person who is running in the train,
Hmm.
he won't be having any velocity.
I
The
am
train
not
is relative to him.
See, I am not saying so. What you are saying is you are fixing different frames within the train. You are fixing two different frames. One attached to the person who is walking, another attached to the person who is sitting. Right?
Yes.
But I am not saying that. The statement each particle has the same speed in its own frame means that a frame where he is moving. So there is an observer in that frame who infers that this guy is moving.
That means both particle have a same frame when we consider its own frame.
No, not necessarily. Uh, well, we'll get to that. Let's first consider this thing, okay? Let's first consider this thing and then move ahead. All right. So for the sake of simplicity, I'm considering two different frames, A and B. Okay, each particle measures that they have the same speed in their own frame, or some observer, a measurer has measured that the particles have the same speed, say u naught in A frame and in B frame. Okay, agreed.
Yes, sir.
Hmm. All right. Now, the effect of collision is to alter the velocities in y direction only. We are not considering any motion along the x direction. Once again, for the sake of simplicity. All right. Now, how the velocities transform from one frame to another. You see, the moment you see, you keep on saying that there is a velocity, non-zero velocity, which is in one frame and which gets transformed to another frame, you cannot really claim that there is a frame where there is zero velocity always. That's not true. Okay, so let me bring this up, a small calculation, so that although in the previous class I told you that it's very easy to see, but nevertheless, I'm going to show you. So the velocity addition, how does it work along y-axis? We had done that for x-axis explicitly, and then I had left by writing down the formula only. So suppose an object moves parallel to y prime axis in x prime. So in this s prime frame, this fellow P is in S prime frame moving along y direction with a velocity uy prime. Okay, where the frame itself with respect to S is moving along x direction with a velocity v. Is this clear?
Yes, sir.
Yes, sir.
All right, fine. Now coordinates of P in S prime, I can say that I'm at two different time, T1 prime and T2 prime. I measure the positions along the y direction, are y1 prime and y2 prime. So what would be the velocity? How will I calculate? By simply this formula. Okay. Now I try to transfer that to the other frame, which is, say, I mean, in our conventional setup is not moving. So according to the Lorentz transformation, this is the conservation, because the relative motion of the two frames is along x direction, not along y direction. So no change in y coordinates. However, there is a change in the time coordinates, and we know that this is how it is related. Here, I think I do not have to tell what is delta t. Delta t is t2 minus t1. Okay, this t2 prime gets transferred to t2, and t1 gets transferred to t1 in the S frame. Okay. Now, if we do a very little calculation of delta y prime by delta t prime, we will end up getting this. Okay, simple substitution. Delta y prime is the difference between these. So therefore, we get this simple formula from where we can calculate that this is the relationship. So uy in S prime frame, the component of the velocity is related to the component of velocity in the other frame in this way. And you can get an inverse transformation nicely. This is the relation. Okay. So with this, now we are going to look at our collision problem, that what is happening over here. Okay, so here's the situation. Try to understand what is happening. Okay, we just did this calculation on how the velocities are going. So before the collision, okay, from the point of view of A, what is happening? The collision was like this. So A will think that I am moving along the negative y direction with a velocity u0. And he will say that B is, so to him, it will look like the particle B is moving with a velocity v towards negative x direction. And as a result, the velocity that in his frame, the velocity of B will be u0 by gamma. Is that all right? You simply plug into this formula. Simple formula. Okay.
Yes.
What is ux? There is ux is 0. So you get uy prime equal to uy into this. This is 1 by gamma factor. So uy prime is uy by gamma. As simple as that. So as a result, that's what A is. This is how A is visualizing the situation before the collision takes place. Same thing, just symmetrically opposite thing is happening in B's frame. B thinks that he is moving in positive y direction with a velocity u0, and he sees that A is moving towards him with a velocity v. As a result of that, to him, in his frame, A's velocity is u0 by gamma. It's shortened. All right. Now, what happens after the collision? After the collision, we know the trajectories. What is going to happen? So in A's frame, now he measures that he is now moving upwards with a velocity u prime, which we don't know at this moment. And to him, it will look like that B's velocity will be u prime by gamma. And just the opposite happens if you look at it from the point of view of B. Okay? It's simple. I guess there is no demon in it. You really do not have to get into too many details. Is that okay?
Can you please why we are dividing by gamma? I mean, why not we multiplying with gamma? In the transformation, you said that uy prime is uy times gamma upon 1 minus ux v by c square.
What is gamma? Tell me what is gamma.
Okay, sir. I got my mistake. It is 1 upon 1 minus v square by c square.
I just said that. So you have to be a little bit, mindful. Okay. Otherwise, for these small things, there is, loss of time. I understand that it requires quite a bit of involvement, but before, jumping immediately, just spend few seconds on figuring out. All right. So that's the situation. Okay. So therefore, if we look at the momentums, or all right, I'm not talking about, so look at the momentum. So this is the situation. In the A frame, these are the velocities. So net momentum is this before and after. This is the momentum. In B's frame, it is symmetrically reversed. Before it is this momentum, and after it, this is this momentum. Okay. However, I mean, so it may look like, okay, fine. So we get a momentum conservation. All right. Before and after the momentums are conserved, it's as easy from here. But hang on. It's not that straightforward. We have little bit of things to consider. So what are they? Okay. So now our task is to find out of this. So this is all fine, the momentum that we have calculated. But what is the momentum in the relativistic regime? I mean, can we simply write it's m into v kind of thing? That is the question. Because you see that the form of the momentums is not really a straightforward mv kind of thing. It is once again getting frame dependent. See, the velocities, although from the classical mechanical point of view, it will be just like, you know, u naught minus u naught. But over here in the relativistic regime, we are seeing the same thing, but in one frame, it is u naught in his own frame. In others frame, it is factored with gamma. So if I want to write down a expression for momentum, which is actually conserved, a general formula, what it would be. That is what we are going to derive next. Is this clear? The motivation that we cannot simply stop here. With this example, we can simply calculate, okay, momentum is conserved and we are done with it. It's not. We are out here to find out that this old structure of momentum as a quantity which is mass times the velocity also still holds. Okay, is it that straightforward, or it has to be modified to incorporate the relativistic effects? So that's what we are going to do next. Okay, so let me show you a little bit of calculation in order to do that. Okay, so we are going to find this out very easily. The point is, before the collision, what is the speed of B in A's frame? See, there are two things. One is the velocity with respect to the frame. So B is moving with a velocity v with respect to A. The observer in A's frame sees that the frame of B is actually moving with a velocity. So there is a x component in the velocity of B. So it is v square plus u naught square plus gamma square because square root of half. And after the collision, it changes. This v does not change, but this fellow changes. It is no longer u naught, it is u prime. Okay. Now, in A's frame, the x momentum is totally due to B, because A knows, according to him, there is absolutely no component of velocity motion along the x direction. So therefore, if I want to conserve the momentum along x direction, this is the relationship that should go. However, here you see, I have made a dependence of m on this speed of B, omega. Okay, do you agree to that? So mass,
Yes, sir.
mass times velocity, the velocity is same. I have, for generalized purpose, I have taken that mass is dependent on this velocity. Okay. And this is a scalar quantity yet to be determined. It's analogous to Newtonian mass, but which can depend on the speed omega. Now you see, it's very easy from here to follow that omega is equal to omega prime. Why so? Because on both sides v cancels. And then if these two quantities, these two masses are to be equal, then the only way they can be equal is if the two speeds, omega and omega prime, are equal to one another. Got it? Now, if
Yes, sir.
omega is equal to omega prime, then what else? U naught, u prime is actually equal to u naught. All right. So this is the first result that we establish. Fine. So we identified what is U prime. U prime is actually U naught, nothing else. Now we are ready to define the momentum. So here we have included the velocity dependence in mass. So I write a generalized form of the momentum that it is still in the mv kind of form, but now this mass has got a dependence on the velocity. Now if we look at the conservation of y momentum with respect to a, we had looked at conservation of x momentum with respect to a. Now we are going to look at conservation of y momentum with respect to a. So we simply write these things, okay? And from there, what we get out is that this m omega is nothing but gamma m u naught. See, the velocity before the collision, so it is, you see, there are terms like m dependent upon u naught and m dependent upon omega. I have written both of them. Okay, is this clear to understand that why this mass has been taken to be in one term, it is dependent on u naught, and in another it is dependent on omega?
Yes, sir.
Yes, sir.
Right. Okay. So from there, this calculation we find out that the velocity dependence of mass can be written down in terms of this. Okay. So we get an expression for this unknown quantity m as a function of omega. Now let's examine. So in the limit, when this u naught goes to 0, what happens? M u naught goes to m0. Okay. So that we take as the Newtonian mass, or we call it as a rest mass of the particle. That is in its rest frame. In its rest frame. The rest frame is something where a particle is not in motion, not moving at all. That we call as the rest frame or the proper frame, whatever. Okay, so in that frame, the mass of the particle is given as m0. So in the limit, now in this limit, when this u naught goes to 0, this omega is equal to v, omega tends to be v. So m v is equal to gamma m. Okay, is that clear? Just the mathematics.
Yes, sir.
So what does this mean? Now, where from this mv comes? You see, the v is the paramount thing. The entire structure of relativity is on two inertial frames. One of them is moving with respect to another with a velocity v. So by this, what we established is that the mass is not the same in both the frames. You identify the frame, which is the rest frame of the object, its mass will be m naught. But you identify the other frame, which is not the rest frame of the object, its mass is actually modified with this factor gamma. So mass is not a constant in special theory of relativity. So mass depends on the speed. Okay. This is once again another mind-blowing result, which you probably couldn't anticipate, or it's difficult probably to sort of conceptualize. But in this small example of elastic collision, it comes out really nicely. All right. So therefore, we are ready to redefine things. And here we go. So now we can define the momentum in the relativistic regime in this form. Okay. And we can show that the momentum conservation law is valid in all inertial frames. I mean, of course, this is with respect to this example, it's very clear, but we will in the next class show a generalized form. But this is the new momentum. Now, if we interpret this as mass into speed, then the mass becomes this because speed is u. So m naught is called the rest mass. That is the mass of an object when it is in its rest frame, measured in its rest frame. Otherwise, the mass has a dependence on velocity, and the velocity is this. Okay. So it was experimentally actually verified. So in 1907, the scientist Bucharer confirmed the dependence of mass on speed of electron. So now that's once again another kind of really game-changing phenomena that the special relativity could predict and was experimentally confirmed. Okay. So now once we have gotten hold of momentum, the next thing will be energy. That naturally comes because the other conservation law is the conservation of energy. So before we do that, first we need to find out the kinetic energy. First we need to work out the formula for kinetic energy. So here's the way we are going to deal with it. A particle which was at rest is accelerated to a speed u. We define the kinetic energy of the particle as this. That's the classical definition. Okay, there is nothing new into it. Only thing is that now we have to plug in the generalized form of momentum into it. All right, now I'm going to show in detail the calculation. That's here. Okay, can you see this? Can you read this?
Yes, sir.
Okay, so
Yes,
so see, the steps are very simple, and you do not really have to break your head over it. You can look at it carefully later on, but let me just explain. So I simply first substituted P with mu. All right, and then just took the differential form. See, this is in the classical regime, and its m has got no dependence on time. It's only dependent on the velocity. So I take m out. What I'm left with is this. So it's u du. Okay. All right. Now, once you have gotten this, now this u du can be simplified into this form so that you get simply u du. I mean, u dot du becomes u du. And so from there, you can find out the classical relation that the kinetic energy of the motion that is generated due to the motion from point A to point B is simply half mub square minus half mus square. Okay. Now what I'm going to do is I'm going to plug in the generalized form of the momentum into it. So I have put the form of momentum into it, and this dr is replaced with u dt. And then I try to simplify this relationship. Okay. And through these relationships, I end up getting here. All right. So by using this identity. So these calculations you can work out by yourself. And then these integrals are very elementary. One can work them out easily. So we get these relationships, these two terms. Then if I set the UA, the point B is arbitrary, and let the particle be at rest at the starting point. The velocity, initial velocity is 0. And then at point B, it is U. So then this is what you get. And then you simplify, do the algebra a little bit, and you end up getting this result. So the kinetic energy in the relativistic form, it's very funny because there is no V. I mean, we tend to think what? It's half mvb square minus half mva square. Instead, what we do get is there is absolutely no V, no U, nothing. But not only that, we have two terms, certainly the difference of the two terms, but then both of them contains the velocity of light. But then this is the key thing, that in one you have the full mass which has a dependence on velocity. In the other case, it is the rest mass. Now let us see, because this is so kind of strange result, we have to first check that whether it gives the right result in the non-relativistic limit. That is when u is much less than c. Then what we can do is that this m is m naught gamma, and I make a binomial expansion of gamma and keep terms only up to the quadratic one, then I get back half m naught u square, which is the classical result. So then that tells us this formula is absolutely correct. Okay. But then what does this formula then means? That kinetic energy is the difference of two terms. Of course, both of them have to be energy. Otherwise, the dimensions wouldn't match. So how does kinetic energy occur? The kinetic energy arises from the work done on the particle to bring it from rest to a speed u. Okay. So Einstein now jumped into this and gave the very bold interpretation. He said that the total energy of the system is given as this mc square, which can be written down in terms of this kinetic energy, that is the work done on particle. He didn't say kinetic energy, he said it's work done on particle, and the other term is the rest mass energy or the rest energy of the particle, which is the internal energy which the system has acquired due to its mass. Due to it being it being massy, it has a energy stored into it, which is given by this m naught c squared term. So you see, this conceptually, this is very different from what we have learned so far, the way we have visualized energy so far. So let's get back to the discussion of it. I hope these calculations didn't pose any problem. So this is the formula for the kinetic energy. And Einstein said that the total energy is kinetic energy plus rest mass energy. I mean, the work done to bring that particle to that state of motion is given by K, and the other is the rest mass energy. So you can see, you have already heard about it, the physics enthusiasts, that Einstein had proposed that E is equal to mc square, and that was exploited in the first atom bomb. How many of you are aware of that or have heard about it?
Yes, sir.
Right. So this is how it was derived. Okay. Now look at the importance of it. That E is equal to mc square. This is the total energy of a relativistic particle. As simple as that. It doesn't say what energy. It does not say it's mechanical energy, it's heat energy, it's optical energy or any electrical energy, other forms of energy. It doesn't give any reference to that. It's a generalized formula. You change the energy, your mass will change. Okay, irrespective of the form of the energy. This E can represent anything. So the general form of energy really goes beyond classical conservation law of mechanical energy. Okay, so in relativity, the distinction between mechanical energy and other form of energy totally disappears. This formula tells us that relativity treats all forms of energy on an equal footing. Okay, in contrast to classical physics, where each form of energy is treated as a special case. So this is the formula or the generalization of the conservation of total energy as a consequence of the very structure of relativity. And what it tells us, which we have never heard of, that the mass and energy are equivalent. Okay. So a change in energy is basically a change in mass. Whatever you lost in energy is being converted to mass. That's a really bold proposition, but it worked. Okay. And so what we'll show in the next class is that these conservation laws for energy and momentum, they are different aspects of a single and a more general conservation law. So it's not like, that energy and momentum are two very different things, and there are like separate, ideologically different things with respect to the conservation of each of the quantities. Relativity puts them together and shows that it's basically different aspects of a more general thing. Okay, now this fact that this this relativistic concept of energy and the validity of the conservation laws in different inertial frames, we are going to once again show with a example. So up to this point, have you gotten the sort of spirit of this thing? How beautiful this is, how game changer this is,
Yes, sir.
right? Okay, so the example that I'm going to show is that of a inelastic collision. The previous example through which we arrived at a generalized form of momentum was elastic collision. In here, we are going to show the case of a inelastic collision. So here, two identical particles are colliding in opposite directions and they are sticking together. Okay. Now, the point is that if we try to treat that relativistically, what do we see is that there is one frame xy, which is the original frame, let's say, quote unquote original frame, and there is a frame x prime y prime which is moving with one of the particles. Okay, so now suppose if I am in this frame, if I am sitting on this frame of the particles, then what I will see is that when the things that are happening over here is that I will find myself to be at rest with respect to this frame, and this frame is moving towards this. Is that clear?
Yes, sir.
And so over here, the phenomena is what we usually perceive in the inelastic collision, that the two balls have stuck together and have come to a rest. Whereas with respect to this frame, since the frame is moving with a velocity v, so therefore the total body is moving with a velocity v. So it was u, it was v. Before the collision, it was u, and after collision, it was v. Okay. All right. So here I have written down the velocity addition relation between these two frames before the collision. Okay. You can easily make it out. Okay. All right. Now let's look at the calculations, what we are going to do, how we are going to establish the conservation laws. So this is the classical picture. After collision, this is what happens. So initial kinetic energy was mv square, where m was Newtonian mass. Final kinetic energy is 0. So the kinetic energy or mechanical energy is lost as heat. Of course, it's conserved, but we call that it is actually transferred into heat energy. And this is the relativistic situation, which I just shown in the main slide. So this is the relativistic transformation of the velocities, very clear. Rest mass of each particle before collision is, because they are identical particle, before collision their rest masses are m naught I, after collision it has changed to m naught f. So in xy frame we know that the momentum is conserved. That goes without saying. We know that the momentum is conserved. It's easy to see. So what is the initial energy therefore? The initial energy is, you see, this before collision, the mass was this, so relativistic total energy is that. And after collision is this, 2 m naught f c square. Is that clear?
Yes, sir.
So no external work done, so total energy has to be conserved. We are not doing any work. So E naught I is equal to E naught F. Energy has to be conserved. So from there, we get a relationship between the rest mass after collision and the rest mass before collision. And we find out that the rest mass after collision is larger. So therefore, we can say that particles are warmer. Okay. So you see that what we used to call as construct as a heat energy and all that, now it's all about mass. The rest mass has increased. There has been this energy that was lost due to collision is now being transferred into the form of increase of rest mass. That's the first thing. Okay. Now, this m naught f and m naught I, if I sort of make a binomial expansion, they are related this way. So the increase in rest energy for the two particles is this. And you can see that it corresponds to loss of the classical kinetic energy. So therefore, everything is falling in place. All we can say that the kinetic energy is not really lost. We thought that the kinetic energy was lost in the form of heat, but it presents itself as a increase in mass when we enter into the world of relativity. Okay. Now, by first postulate of special theory of relativity, all inertial frames are equivalent. So the conservation laws must hold in x prime y prime frame as well. So in x prime y prime frame, what is the conservation of momentum is simply this. Okay. In the x prime y prime frame, remember one particle was at rest and the other particle was moving with a velocity u. And in that same frame, after collision, this big ball with each one of them having rest mass m naught f was moving with a velocity v. So this is the conservation of momentum. And conservation of energy, before it was the one who was not moving, he had only rest mass energy, m naught I c square. And for the other, the energy is mc square, which is written in terms of m naught I. Now, after the collision, the entire body is moving with 2 m naught f rest mass. So the total energy of the entire entity is m naught f c square, 2 m naught f c square. So, sorry, 2 mf c square. So that's written in terms of the rest mass. Is it clear before I move ahead?
Yes, sir.
Okay. So now it's all about, little bit of calculations. So from equation 1 that we have, the relation between u and v, we can find this out, 1 minus u square by c square, and then do the calculations. Then we plug it into the left-hand side of this thing and ultimately get back this equation identical to equation 3, which was conservation of momentum. So starting with the conservation of energy, we considered that energy is conserved, we get back the conservation of momentum. Because you see that since all inertial frames are equivalent, the momentum conservation is paramount. We started out from there. We wrote down the conservation of momentum law. Then we also claimed that energy is conserved. So we wrote down the form of the conservation of energy. And from there, we showed that yes, we are getting back to the previous one. And you can do the same thing once again. You can do the other way. That is, you can start from the conservation of momentum, and then you can consider that energy is conserved, but you are not sure whether momentum is conserved. So you can start from momentum, writing down, forcing the momentum to conserve, and you get back the conservation in energy. So what it shows that with respect to this example is that both the energy and momentum are conserved irrespective of which inertial frame it is. Okay. So therefore, if one has a kind of suspicion, doubt about whether these forms of energy or momentum really preserve the conservation laws of energy and momentum as we know in Newtonian mechanics, these examples actually elude your fear. Okay. So now we are ready to write down an energy momentum relation in STR. So we combine expressions for momentum and energy. So you see, this is the relation for momentum and this is the relation for energy. And I do a little bit of algebra and get back this result that energy and momentum are related in this way. E equal to p square c square plus m naught square c4. So you see, if there are massless particles like photon is a massless particle, neutrino is a massless particle. For them, this term is 0 because m naught is 0. So then the energy momentum relation is simply equal to p square c square. I'm sorry, I missed one line here. Excuse me, very sorry. This should not give a wrong impression. Should be e square. Okay, sorry. It's e square equal to p square c square plus m naught square c4. So E equal to pc for photon. That's the energy momentum relation for photon, for example. Okay, so these are like completely new results which you haven't really heard about, because you know the Newtonian mechanics, the classical mechanics, it all dealt with mechanical things only. It never actually entered into the arena of light. People just took it for granted that whatever we have done in case of mechanics, mechanical things, is applicable for electromagnetic waves also. So simply, substitute things of mechanical waves with light waves and everything would fall in place. But then what we are seeing is that, first of all, it didn't work. And so when Einstein worked out this formulation of special theory of relativity, it gave rise to a whole bunch of new concepts, new relations even. So for example, this. Okay, so these are the energy and momentum important expressions that one has to keep in mind. Okay, in the next class, what we will do is basically we'll show that these conservation laws for energy and momentum are different aspects of a single generalized conservation law. We would be using a new technique, different technique to do that. And that will also show that what are the things that are invariant under special theory of relativity. What I mean to say is that, although none of you have actually told me this, but I'm sure in some of your mind, this question has been hovering around, that you are saying that length is not an invariant quantity in special theory of relativity. Time is not an invariant quantity. So what is an invariant quantity? That question definitely must pop up in your mind, because these invariants are key things in the physical world. So if special theory of relativity is applicable in a physical world, and we have seen that in the world of the high energy particles or distant stars, the relativistic effects are important, then invariance of such basic quantities must be there. How do we get that? What are those quantities? So those we will be studying in the next lecture. And we will, of course, consider the force, what happens to Newton's second law of